Lovely. Right, grand. So what I'll do is I'll just pop up I've made a few changes to the PowerPoint presentation. I'm just going to run through it because it's the easiest thing to do. Now there's some handy images and notes in the present now. There we go. Your entire screen. There we go. And then I'll just do that screen. Right. Are you seeing my screen now? Are you?
Yeah.
Yeah, it should be coming up now. Hold on a second. Right, can everyone see my screen now?
Yeah.
Grand. Right, so in that case, just go on to the PowerPoint. There's some handy notes in the book as well. Okay, so right, running through the PowerPoint, like the first few slides are brutally simple, and the first few questions that I gave you was brutally simple. Basically, materials and the structure of materials. Basically, looking at your liquids, how your atoms are structured. You did all that in junior cert science, so I'm not going to go through it again. Basically, you have your nucleus and your electrons around it, right? Periodic table, not going to go into it. It's simple science. Now, what we're looking at is basically, I did ask you about the three types of bonds: the covalent bond, the ionic bond, and the metallic bond. Now, the first two, in metalwork, we don't look at them only until polymers. So in this, the first covalent ionic don't matter. The only one we're looking at is the metallic bond. So we could skip through we can skip through basically your covalent bond, the ionic bond. It's handy to know them, and it's handy to know the principle of them. We're going straight to the metallic bond, and basically what it's saying is that in the metallic bond, what happens is because electrons in metallic atoms, the electrons only have a loose tie to the atoms. When metal atoms, when I'm talking about metal atoms, I'm talking about iron, I'm talking about copper, gold, aluminium, tin. All of them arrange themselves in a set pattern, right? And what happens is you have the atoms sitting in place. So if that was copper, their copper atom, copper atom, copper atom, copper atom, and all the electrons just move freely around them, and this is called the cloud or the sea of electrons, right? So that's the first thing you need to understand, that all metallic bonds, all metals arrange their atoms in a very structured manner. Basically, that there's lines of atoms, there's rows of atoms, and it's like a grid, like building blocks on top of each other. All right. So that's the most important thing to keep in mind when we're talking about the metallic bond. Now, the fact that they arrange themselves like that means that they have a few properties. So obviously, if the electrons are just loosely tied to atoms and they can move freely around, if we were to connect a battery to one side, positive to one side, negative to the other side, and basically what you're having is you have a flow of electrons. Instead of them flowing freely around the place, you'll see the electrons start to actually move from one side of the material, flowing through to the other side as the battery. So essentially, that is your conductor. That's why metals make a good conductor. So, and then the other thing is, the thing that we looked at this week was atoms being able to slip over each other. So this row of atoms being able to slide or slip over the top of these atoms. Basically, when the metal is bent, makes metals ductile, and you're able to bend them. Whereas, say for example, glass, which is a different structure, if you go to try and bend it, it'll snap because the atoms aren't allowed to move over each other. So keep those few things in mind, right? So that explains why the properties. That's just to try and give you an idea why the properties of metals are. They're a good conductor. I've explained that just a second ago. They're malleable because the atoms are able to slip over each other in lines and rows. Electron donors, which forms oxide, basically that's where the electrons can be given off and cause oxides or rust, okay, where the material breaks down. Capable of making a shine, grand materials, high density, yeah, the atoms are packed in tight. Materials with high tensile strength, and then solid at room temperature, except for mercury, right? So other examples that would be water. Water is liquid at room temperature, okay? Now, and just more onto the properties of metals. We'll look at the properties of non-metals. Sorry, we'll look at the exact properties in further down. Okay, Semi-metals, here we're talking about alloys. We're talking about materials that can alloy with a metal and a non-metal. Can anybody give me an example of a metal and a non-metal mixing together? Anybody that has the mics on? No?
Brass.
Brass is actually not, because it's two metals. It's binary. Binary means two things, or simple. So or binary just means two metals. Okay, so that'd be copper and tin, right? Or copper and zinc, whichever. An example would be steel. You have iron and you have carbon. Carbon is not a metal, so semi-metals or compound metals. All right. Now, states of matter, this is simple. Solid, liquid, and gas. Easiest one to remember is your, again, water. Going from solid ice at 0 degrees, then as we heat it up from above 0 degrees at room temperature, it becomes liquid, and then above 100 degrees, it becomes gas. The exact same thing happens to all metals. If you take copper at room temperature, it's solid, right the whole way up to 1100 degrees, or about 1093 degrees. It becomes liquid. You heat it up even higher again, I think it has to go up to about 17,000 degrees. It becomes a gas. It becomes a lethally dangerous gas because you have a gas which is containing metal atoms at superheated temperatures. So it'll burn through anything, but it's still a gas. Okay, so the same applies to most materials. So you have a solid where the atoms are packed in tight and very little energy, liquid where they have a little bit of energy and they have a little bit of movement, and gas where they have a lot of energy and you have the atoms vibrating very fast and they're able to move freely around the place. Okay? So when we talk about metals, the next thing to look at is the solidifying. Now, I gave you a question where I asked, how do metals solidify? And some people gave me back atoms and stuff like that. When they ask that question, they just want to know that in a metal, if you start a metal solidifying, and this happens to water as well, if you let water cool, it'll start to cool in little pockets, and in this case, it's called a dendrite. Okay, tiny little dendrite. What happens is material just starts. So if you think about this as a little bit of solid and all surrounded by liquid, that grows, branches grow out in all directions, and they're called secondary dendrites, are the ones that come out off the sides, and then tertiary are little small ones again. And they just keep growing, and that's just essentially solid material growing where it is liquid, and it keeps going until it forms a solid nugget of metal. Okay, and it's important to remember these solids. If we go back up here, they're atoms. They're atoms that are slowing down and joining side by side to each other. So that's what's happening here. There's an atom slowing down and it's attaching onto others and it's attaching onto others and it's creating a big lump of metal. It's just the atoms sitting beside each other. All right. So if we look at in reality, so if we take a piece of metal and you cut it and then you shine it up really, really, really shiny, and then you look at it under a microscope, this is what you'll see. And this applies for every single metal. You'll see what are the grains. So each one of these grains started out as a dendrite, as a small dendrite, and then grew into a grain. So it looks like this. If you look at galvanized gates, you'll see a pattern like that. Each one of those little flakes is a grain, okay? And within each grain, your atoms are arranged in lines and rows. So this is where everything is coming in, the principles are coming into what we're going to talk about in a minute, all right? And then within that, we have to look at how the atoms arrange themselves. What way do they arrange themselves? Are they lie on top of each other in rows, or do they sit down into each other? That is purely dependent on which metal you're talking about. If you're talking about gold, gold sits down very tight and it's very dense. So it's FCC, right? Face center cubic. I'll look at that in a minute. Or if you're talking about iron, it's a little bit more bulky, it's not as dense, and the atoms are spread out more. So the atoms here would be spread out more, and it's BCC. So it's just the way each of the atoms, the metal atoms, arrange themselves. Is everyone okay? I'm not losing anybody, am I? Do we have concurrence there? Is everyone all right? Yeah, grand. Okay, right. So we'll carry on. Right. So in that case, that's why we talk about BCC and FCC and CPH. So basically, body center cubic, and that's where they arrange themselves in either the atoms sit like this, where they have layers sitting on top of each other, all the layers. That's just this arrangement here is BCC, and then you have the little cube in the corner. That's your BCC. Where they've just taken out the little chunk in the corner or a cubic square, and this is the arrangement that they see when they take out that square. If we look at FCC, they take out the same square. Then there's atom in the middle, and because they're packed tighter, there's atoms on each face of the cube and each corner of the cube. Whereas in BCC, they're packed a little bit further apart, and there's just, when they cut out that cube, you've got the atom in the middle and just an atom on each corner then. All right? Now, that's your FCC and your BCC, right? So, and as I said, if you're wondering how does this happen, it depends on the metal. FCC or BCC being iron, being titanium, and your more and brass and tungsten. All of them are hard, brittle, less ductile, okay, materials, and they form BCC. The atoms just arrange themselves in this way in those materials. And then if you look at the FCC, they're packed in tighter, which makes them softer and more ductile. That you're talking about your gold, your aluminium, and your copper. The atoms in those materials just arrange themselves in this fashion, all right, because of the electrons that are the structure of their atom. Okay, so and then it's important to mention the packing factor. Basically, that it's 68%. That means that if we take that cube, 68% of it is taken up by atoms. The other 32 is taken up by empty space. Whereas FCC, it's 74 is taken up by atoms, and the other 26% is empty space. All right. Now, what difference does that make to us?
Is it just me or is he... Sir, I think you're lagging a bit.
Is my voice a little bit behind the?
The mic, like, yeah. Wait,
Right.
is it just mine? Adam, can you hear it? No, I can hear it. Alright.
Oh, is it lagging for you as well, Adam?
Small bit, like.
Small bit. What I'll do is aye, the video, I'll send out the video anyway. It's recording now anyway, so if it's not working too well, I'll try and keep it short, so I won't be going for much longer, lads. Okay. So now, the question we need to ask is, why do we need to know this? Why bother? Like, what importance does this have? The importance that it has is because the way the atoms arrange themselves, dictates what the properties of each metal has. So, BCC, body center cubic atoms, are arrangement are usually hard, brittle, and less ductile. FCC are usually more ductile, softer, and much easier to bend. Okay, so now close pack hexagonal. Again, you don't need to look at it. You don't need to know as much about it, but know that the tighter the atoms packed together, the more ductile the material is. Close pack hexagonal is packed quite tight, so therefore it's quite ductile. All right. So now, next thing we need to look at is slippage. Now, again, I'm going to skip a couple. I've modified these slides, and I'll send them on to you. Basically, they're a little bit more updated, right? So, say if I skip down to here, right? So we have slippage in BCC and FCC. So this is BCC. Now, hold a second. We were talking about BCC as a cube a minute ago. How are we getting this arrangement here? How we get this arrangement is if we go back up to BCC, just here, that previous view, that view of this part here where the atoms are just in rows, all we're doing is we're looking in at the side of the structure. We're just looking in at this direction here, and we're taking the top row and the bottom row. So that's top row and bottom row. Okay? So that's how they arrange themselves. So in BCC, because the atoms are more spaced out, the atoms will sit down into each other more. There's still more space there, but they'll sit down into each other more. Whereas if we look at FCC, they're packed much tighter together, so therefore they don't sit down into each other as much. Okay, and again, that just is looking at the rows, looking at the side of the rows sitting on top of each other, or the layers, the lattice. Okay, so that's why I've done up this image here. So slippage. Can anybody tell me what is slippage? In reality, when we talk about slippage, when a metal slips, for a metal to be able to slip, what are you doing to it? I'm going to wait for a response. Someone should go on.
No, is that like what is slippage like? Is it kind of like a thing in between all the atoms?
Yeah, well, in reality, so I'm asking to yourselves now, what's slippage? Like when I'm like, what am I doing to the metal for to cause the atoms to slip?
Lubricant.
Not quite. No, lubricant has nothing to do with it. Nothing to do with it. And I'm here to throw out any guesses. I don't care as long as they're decent and not taking the piss. So the answer is I'm bending the metal, right? All you're doing to cause the metal to slip, to cause atoms to slip over each other, is you're bending it. So if the atoms are moving over each other, it goes back to what I said earlier on. If the atoms are forced to move over each other, that happens when you bend a metal. If you took a piece of brass bar or copper bar and you just bend it at 90 degrees, for that to happen, the atoms have to be able to slip over each other within those grains that we talked about earlier on. Okay? So say for back up to here, if I was to bend this piece of metal here, that's your grains, what would happen is these grains, if I bent this at 90 degrees round like that, these grains would stretch and these ones would compress, and basically all these grains would be slipping. All the atoms within these grains would be slipping to allow them to bend. Okay, so that is what slippage is. And if slippage happens easier, then it's a soft ductile material. If it's harder for it to happen, it's a tougher, stronger, more brittle material. So this is BCC, this is FCC. This is the way the atoms arrange each other in layers in BCC, and this is the way the layers sit on top of each other in FCC. Which one's going to slip easier, lads? Think about this as speed bumps. If this is the wheels on my car, and these are the speed bumps, if I have to stand behind the car and I have to push that car to get over this speed bump or to get over the FCC speed bump, which one's going to slip or move easier?
The FCC. I mean BCC.
No, no, no. You're right. You're right the first time. FCC. Look, there's less of a bump there.
Oh, the bottom one.
Ah, yeah.
Yeah, the bottom one.
Aye, the bottom one. There's less of a bump in the FCC. The atoms sit down into each other less. So therefore, it'll take less force to apply to move these atoms, meaning that FCC is going to be soft and ductile. Actually, I meant to change these to the properties. Soft, soft, ductile, here, properties. Whereas here, the atoms are not going to slip easily. So therefore, they're going to be a much more stiff, strong, tough, or hard material. Right? So that's when we talk. If I ask you to tell me difference between slippage in FCC and BCC, these are the two diagrams you draw. You say that BCC atoms are spaced further apart, they sit down into each other further, meaning that slippage is much harder. FCC, they don't sit down into each other as much, they're packed much tighter together, meaning that there's much less force required, making them much softer, ductile, and weak materials. All right? Is everyone okay with that?
Yeah.
Sweet. Okay, so then there's just a few more diagrams, and then I just threw in a few graphics of the atoms actually arranged in the actual bulk, grain or crystal there. Okay, when I talk about grains, the word grain and crystal can be used for the same purpose. All right, so if I say grain or crystal, I mean the same thing. I mean a piece of metal, which is the atoms are arranged in a pattern. Okay, now here we're looking at basically slippage. Like this is basically this is your grain. This is the 3D image of your grain, and if we apply a force one way and the other way. So basically, if we're trying to bend the material, if we grab the bottom part and we're pushing the top part across to bend the material, what will happen is slippage. The atoms basically slip across this way, and you're left with atoms having slipped. If I keep doing that, then this cube becomes way more elongated and stretched. That's exactly what happens to the grains. Okay, that's what would happen here. Okay, so I'm going from a cubic space. I roll the metal, I squeeze it, the grains become long and elongated and stretched. Okay, that's for this to happen, slippage has to occur. All that's happening here is slippage within the atoms of the material. That's why slippage is so important. An example would be here's copper and here's iron. Copper soft and ductile, it'll bend all day for you. You go to try bend iron too much or brass, it'll snap because slippage is much more difficult to happen, okay? So, and then here's just another depiction of that exact thing, right? Where you have your lines of atoms and then they slip across each other. This is the other graphic that they used, that one there, all right? So that's slippage covered. Hopefully it's clear in everyone's head. The next thing we needed to talk about was that we've talked about this. These are just a few more notes on the same thing, like defects. So if we take the other thing you had to talk about was defects. We talk about crystals. We're looking back up here, and I'm giving you pictures like this, where the atoms are arranged all perfectly, all happy, and then here, where the atoms are perfectly arranged. That never happens in reality. In reality, it'll get the majority of that to be okay, but there'll be lots of imperfections within the crystal. There'll be atoms missing here and there, or there'll be or foreign atoms, imperfections being included in it. If there was a wee bit of copper atoms added in there from when the furnace was being used for melting copper previously, whatever, or dirt, whatever, right? So this is where imperfections come in, okay? So defects within the crystal. And I'll talk about what impact that has. Your defects are your line defect, which is your dislocation, which is where there's a line which has been discontinued or isn't, and this will cause a weakness in the crystal. It'll mean that because this one guy can slip onto all the other ones, it causes slippage to happen easier. And if slippage happens easier, it means the material is soft and ductile. So it's weakening. This one will weaken the material. Whereas if we look at some of the point defects, which are, again, looking here, this is a perfect crystal, happens very seldom. This would only happen in very, very expensive materials or high risk components. Say, for example, a turbine on an airplane, the engine on an airplane. The metal within the blades are single grain technology, meaning that they're perfect, right? You have to pay massive money for that. So in reality, there's lots of imperfections. A vacant site defect. It's where an atom is missing in the structure. And basically what happens is it strains the electrical or the electromagnetic bonds, and if there's a strain there, slippage will be restricted. So this actually strengthens the material. The same applies for a substitution defect. And this is where there's a foreign atom in the middle of the structure. And again, as you can see here, it strains the microstructure, making slippage more difficult. Again, it's strengthening the material because slippage is restricted, and especially interstitial. Interstitial, when it's going into the space in between, it's restricting movement, it's strengthening the material. Okay, and that's all you need to know. That's that's the crystal defects, and that's how it works. Okay, properties of material, we've talked about them already at length, so I'm not going to go through them. I'm going to skip on. So the last thing I'm going to talk to today is thermal equilibrium diagrams. And lads, these are going to come up in your exam. I'm telling you right now, I'm going to give you a thermal equilibrium diagram, right? So listen up. I'm going to give you everything that we've done in the last couple of weeks. The exam is going to be based on that and a little bit of stuff that we did previously in fifth year on polymers, welding, and stuff like that, right? So alloying, thermal equilibrium diagrams. So I'll just show you them to start off. That's a thermal equilibrium diagram. Basically, you have all the temperatures along the side, and you have all the different percentages. Basically, on one side, you're going to have, say, let me think of a good one, copper and tin for brass, right? Copper and tin for bronze, sorry. Copper and tin for bronze. So here you're going to have 100% copper, here 100% tin, and each step in between you're going to have like 10, 90, 20, 80, 70, 30, 40, 60, 50, 50, all the different compositions. And basically all it does is tell you for 50-50 copper tin, if we go up, then this is the temperature that it starts to melt at. It goes through the melting stage, and then once it goes through this temperature, it becomes liquid, right? So this is a very simple thermal equilibrium diagram, but it's important, and we'll talk about it later on, not now, okay? So where do we get these from? Basically, if we look at a simpler graph, this is called a cooling curve. And this is we take 100% copper and we take it from 1500 degrees and we just watch what happens to it as the temperature drops. As the temperature drops, we just see the over time. So we're just saying along the bottom is time, up here is temperature. And this is what a cooling curve is. And it's off one specific percentage of copper. So this is pure copper. The reason that I know it's pure copper, I'll explain why I know it's pure copper in a minute, right? So here we have the furnace is on, the furnace is on, the furnace is on, the furnace is switched off. As soon as you switch off the furnace and you take the copper out and you leave it cool at room temperature, it's going to cool. The temperature starts to drop. Over time, the temperature starts to drop. It continues to drop until eventually it gets to the solidification temperature. For copper, as I said, it's 1093 degrees, or somewhere around there, depending. And what happens is, can you tell me what happens to a pure material once it starts to solidify? Why has this temperature stayed the same? Can you tell me what's that called when a material temperature stays the same when it changes from one state to another state? So basically changing from a liquid to a solid. Can you tell me? I'm going to wait for an answer. No, it's latent heat. So that term is latent heat, where a material will stay at the same temperature as it cools. Once it's fully solid, then the temperature will drop again down to room temperature. Okay, so that's a cooling curve. And basically, what they do is, I've talked about latent heat here, Grant. What they do is, they take this is a graph. This is that graph, is that one there, right? And here, what they've done is they've taken pure copper and pure tin, and then they've basically said that this is what happens if we for the cooling curve for pure copper. And this is the one that if we add in 10 or 20% tin. And here's what happens if we add in 40% tin. And here's what happens if we add in 60% tin. And here's what happens if we add in 80% tin. And they basically look at the temperatures that solidification starts and ends. Where solidification starts and ends, starts and ends, starts and ends. And they put those here on the graph. On the graph where solidification starts and ends. Solidification starts and ends. And this, each one is a cooling curve. You combine all your different percentage cooling curves to give you one thermal equilibrium diagram. Okay? That's it there. So you need to be able to tell me what a thermal equilibrium diagram is and what a cooling curve. If I ask what's a cooling curve, cooling curve is the study of temperature of the material over time and the changes that happen. A thermal equilibrium diagram is the study of the solidification of all the different compositions of an alloy. Right, I'm going to leave it at that, lads. I'm not going to go any further because you don't. I'm not going to include any more in an exam. I'm going to stop the recording there now. 1 second.